Welcome to The Explainer. Today we're tackling a surprisingly tricky puzzle that hides in plain sight inside one of the simplest shapes imaginable. So what is the angle between any two main diagonals of a cube? Just by looking at it, it's tough to guess. Is it 90 degrees? Maybe 60? Well, the answer is not what you might expect. And to find it, we can't just use a protractor. We need a powerful mathematical tool. Okay, so to solve this puzzle, we need to think a little differently, almost like a physicist. We're going to build a toolkit from the ground up to crack this geometric mystery wide open. First up, we need to get a handle on our main tool. So what exactly is a vector? Think of it as an arrow in space. It's not just a number. It tells you how much and which way. This is perfect for describing things like displacement, velocity, or force. But, an arrow just floating around in space isn't all that useful. To handle vectors precisely, we need to place them in a 3D coordinate system using a basis set. This basis set lets us turn our abstract arrows into concrete coordinates. We get three directions, x, y, and z, at right angles to each other, represented by these little vectors called I, j, and k. So a vector like v equals 2i plus 3j plus 1k is just a set of instructions. Now, let's move to our secret weapon. And this is the whole key right here. This formula, called the scalar or dot product, is the magic link between the components of two vectors and the angle between them. This is basically our treasure map, you see? Our goal is to find the angle theta. And if we can find the values for the dot product a dot b and the lengths of our two vectors, odd a and odd b, we can solve for it. All right, with our toolkit ready, let's apply it to the cube and solve this puzzle step by step. Okay, we've got a clear 5-step plan. Following these steps will lead us directly to the answer. Let's start with step 1 and 2. So first, let's just stick one corner of a cube with side length 1 right at the origin, 0, 0, 0. Our first diagonal, D1, goes from there to the opposite corner at 1, 1, 1. So its vector is super simple, 1i plus 1j plus 1k. For the second one, D2, we'll pick the diagonal going from 1, 0, 0 to 0, 1, 1. That gives us a vector of negative 1i plus 1j plus 1k. Okay, we've defined our two diagonals. Now for step 3. Let's compute their scalar product. We just multiply the matching components and add them up. So we have 1 times negative 1 plus 1 times 1 plus 1 times 1. That all comes out to just 1. Easy enough. The scalar product is 1. Now for step 4, we find their magnitudes using the property that a vector's magnitude squared is just the vector dotted with itself. For D1, we get 1 squared plus 1 squared plus 1 squared. That's 3. For D2, we get negative 1 squared plus 1 squared plus 1 squared, which is also 3. So as you'd expect, the diagonals of a cube have the same length, the square root of 3. And look at that, we now have all the pieces we need for our final step. Let's plug everything back into that magic formula. The dot product was 1. The product of the magnitudes is the square root of 3 times the square root of 3, which is just 3. So we have 1 equals 3 times the cosine of our angle. We just rearrange that, and we find that the cosine of the angle is 1/3. And if you punch that into a calculator, the inverse cosine of 1/3, you get an angle of approximately 70.53 degrees. There it is. Not 60, not 90, but this really cool, unique angle that comes right out of the cube's own geometry. This is the angle between any pair of the cube's main diagonals. So yeah, we solved a fun puzzle. But this shows something way bigger, right? It's about the power of vectors to describe the world around us. I mean, this method isn't just for geometric brain teasers. It's a foundational concept that's used to build the physics engines in your favorite video games, to design skyscrapers and bridges, and to understand the laws of nature themselves. It's a great reminder that sometimes the most elegant solutions come from looking at a familiar problem from a completely new angle. It really makes you wonder, doesn't it? What other simple shapes hold complex secrets just waiting for the right tool to come along and unlock them? Thanks for joining this explainer.